Let's see here. Oops. There we go. Okay. Nice to see everybody. I'm glad at least 7 of you survived the first homework, apparently. To those who are watching on the internet, because many of you guys send me questions like a week and a half late, that's cool, but if this room gets much smaller, then we're going to like start doing something annoying like delaying the recordings, because like really, there's nothing worse than teaching to an empty room. Don't do that again. Yeah, years ago I taught this class at Stanford, and Stanford has one of these like online education things that kind of predated everything at MIT, and there I literally taught to an empty room many years before COVID, and it was not a fun experience. Like, you want to like pack a cardboard cutout of the rock to like sit in the front of the room or something. In any event, so let's see. In terms of announcements and things, how many of us have downloaded homework 2? Not everybody. How many of us have at least run the starter code? How many of us have run the starter code successfully? How many of us have finished homework 2? Too bad. Okay. Right. So the good news is that it appears the starter code hasn't had catastrophic failure yet based on data collected roughly 18 seconds ago. To those of you who have not tried the starter code yet, please just spend 15 minutes downloading for me. Okay? To download it and give it a try, because this is computer graphics code, meaning that with high likelihood it will fail in some weird catastrophic way that we haven't anticipated. That's just how it is in this particular domain. You guys are equipped to start the homework now. In particular, there are some theory problems you can just play with. And moreover, I think a thing that you'll realize in this class, if you haven't already, is that like the contents of the lecture and the homework are ever so slightly separated, in the sense that I feel like a lot of work we have to do in lecture is showing that assorted matrix factorizations exist and kind of thinking about where they came from. But the reality in numerical analysis is very rarely do you actually code up one of these factorizations. And in fact, if you have, there's probably something that went wrong, unless you are a specialized person in exactly that, right? And so the reality is a lot of the homework is trying to get you to think about how to use these tools, and a lot of the lectures are telling you what the tools are. Right? And so from that perspective, it's actually pretty straightforward to get an early start. Or if you want to like put it in a negative light, what I'm saying is the lectures don't give you anything useful. Okay, any questions about that? Fabulous. Okay, so in that case, today we are going to continue our intrepid exploration of numerical linear algebra, surprise, surprise, and give you yet another way to solve a linear system of equations, because we need many of those. In case you haven't figured it out by now, like these are super important, hella important. And because of that, we got to think through these things, think about the different algorithms and structures that show up in our problems, and why we might prefer one of these techniques to another, depending on the particular setting that we're in. Okay, so let's set the stage for our story today, which, by the way, really maps on, again, to our undergrad linear algebra class. It's just we're taking all of these boring things that you did by hand and codifying them in a way that you never have to do them again. Right? That's our goal in the first, I'd say, like third of this class. The second and third thirds of this class, I think that begins to depart. Like, I don't think in undergrad multivariable calculus spend a lot of time like solving weird root finding problems, but like in this case, it really does map on pretty clearly. So if you recall, our basic, to give you a little bit of a review so far, our basic story is we started with linear systems of equations, and we derived a matrix factorization whose job in life was to basically codify the steps of Gaussian elimination, which is what you've all done by hand 1,000 times on paper, right? And that factorization was LU. And in the specific case, when your matrix is symmetric and positive definite, we were able to kind of streamline LU a little bit and just basically keep around L in some sense. And that gave us this other factorization called Cholesky, right? Which is basically LL transpose. So why did we do Cholesky? Well, essentially, we motivated Cholesky factorization by thinking about one problem which shows up every time, all the time, in everybody's everyday lives, which is the following. You haven't noticed, like, 2/3 of the lectures we have in this class are going to start with the same equation, which is as follows. I'm sorry that my handwriting is somehow worse than it normally is, but hopefully the good news is you all know the equation I'm going to write on the board, which is the least squares problem. And why did we do Cholesky factorization? Like, why was that sort of a feasible option in this particular case? Well, we showed by taking the gradient of this and setting it equal to 0. In case you haven't noticed, like, by the number of times I've repeated this, like, you guys are always asking me what's going to be on your midterm. I don't know. Okay, so we derived a very particular set of equations, A transpose A, X equals A transpose B. These equations are called what? On three, everybody? 1, 2, 3. The enthusiasm is not there today. But in particular, this is a linear system of equations that is square and invertible so long as the columns of A are linearly independent. And as soon as we get to this point, basically we can throw this matrix, not A, but rather this matrix A transpose A, into our favorite linear solver. Like LU is perfectly fine, just a little inefficient for this case. And out comes the solution of this optimization problem. Right? Because again, our goal in life is to start with this one tool, which is inverting a matrix, and show that by just like kind of giving it bells and whistles, we can solve bigger and bigger sets of problems. Okay? So at the end of the day, in some sense, what we really solved was some other linear system, Cx equals D, right, where C was A transpose A, and D is A transpose B. Yep. So we've talked about a lot of algorithms, and then you might notice in the previous lecture, we kind of took a step sideways, laterally, for those of you who do sports, I think. And essentially, what did we do? We kind of put aside our algorithms, we talked about conditioning, right? And in particular, we tried to think about when are linear systems of equations easy or hard. And one thing that we didn't do was kind of map that onto the language of our last couple lectures. Like think about what does, when does our condition number and all this kind of stuff actually inform us about why least squares problems might be easy or hard. And in fact, one thing you may or may not know is that numerical analysts often grumble at the normal equations and say this is actually not a system of equations that you could solve or should solve as written. And so I think the right way to kind of begin our lecture today is to justify why. Okay? And we're going to do so in extremely hand-wavy kind of heuristic fashion. So first of all, notice that the condition number of a linear system in general, in a generic norm, just to be totally generic, is what? Do you guys remember from our last lecture? It's the product of two things. Yes? That's right. Or in this case, I sneakily have replaced A with C, which is actually important because for today's lecture, A is going to be the thing in the least squares problem. So as you say, this is the norm of C times the norm of C inverse. This is the sort of generic formula for the condition number. The one that I think we all know and love is specifically when you put the induced to norm of a matrix. It's a fun phrase, right? You can share it at parties and like bar trivia, which is going to give you the ratio of the largest to the smallest eigenvalue of C, which intuitively kind of makes sense. Like an ill-conditioned matrix is one that like operates on many different scales, right? Like in some directions it makes things really big, in some directions it makes it really small. Cool? Okay, but in particular today, we don't care about just generic matrices C, we care about matrices that we're going to use in solving least squares problems. Okay? So in particular, the thing that we really care about is A transpose A times the norm of I guess A transpose A inverse, right? This is a lot of A's. Yeah, and that feels like a problem. We're multiplying a lot of numbers together. By the way, sanity check, condition numbers. When are they good? Big or small? We're going to be thinking about that a lot today. So like, let's get it in our head now. A small condition number is a good thing, yeah? And in general, like think about identity matrix here, you're going to get a condition number of 1. So for most condition numbers, it's lower bounded by 1 and the identity matrix. And in fact, we will see other matrices, hint, spoiler alert, have condition number equal to 1. Yeah? On the other hand, big condition number is bad news. Okay, now if you'll remember, as part of the proof that we wrote in our previous lecture, we had this, in that case we wrote an inequality, but like it turns out you can kind of bound it with some constants on all the other sides to make it more of an approximation, which is that we have expressions like this, which are really products of matrices whose norm we're trying to compute. And for now, this is obviously not the case we care about in least squares, but let's think about A as being square and invertible. The one thing that you can show pretty straightforward is that the norm of this product is like roughly on the order of the products of the norms. We haven't proven that to be 1000% clear. You should go back to your formulas and actually kind of convince yourself that that's like kind of a reasonable thing to say, at least for invertible matrices. But roughly, this expression is the norm of A transpose times the norm of A. By the way, our definition of condition number works for non-square matrices. At least, I'm sorry, I said something wrong. Ignore that, wipe out the last like eight words. Okay, times the norm of A inverse transpose times the norm of A inverse. Okay. I have not justified this formula. I want to be 1000% clear about that. But I think you like certainly we can like at least upper bound it using the stuff that we did in our last lecture, right? It turns out you like up to a constant you can also lower bound. Okay, everybody with me so far? I find if I acknowledge my mathematical weaknesses, then you guys get less uncomfortable with me. Okay, what do we notice here? By the way, do you think that like transposing a matrix really affects its norm? No, like for example, in the 2 norm, like it's really obvious, right? That like transposing a matrix doesn't affect its singular values. So in particular, let's kind of couple our terms together, maybe like that guy and that guy. And what do we notice? That this is roughly the condition number of A squared. So again, to repeat, like the really fishy step here that you should justify at home is this one. But like I think you guys can certainly buy that it's upper bounded, and that's already like kind of bad news. Yeah? Okay. Now I said bad news. Why is this bad news? Well, if my linear system was hard to solve to begin with, right, notice that like if A is square and invertible, I can still write the normal equations down and solve it that way. Like it would be a dumb way to solve a linear system, but I could do it. But what happens to the conditioning of my problem in that case? You're making an interesting gesture, but I think you actually agree with me, which is that it squares. It gets really big, right? And we're going to draw some pictures to give some intuition why. But essentially, this is the big challenge. Like, you know, we've proven we can solve these squares with the normal equations, but we have not shown whether we should. Yeah? To quote Batman? I don't know. Right. So essentially, this is the challenge here, is that like, ta-da. Oh no. Okay. Roughly, when you move from solving your original problem to solving the least squares problem, you can do that, and in like infinite precision arithmetic, whatever, life is good. But from a conditioning perspective, your problem just got a lot worse. Okay. And so that's really the issue here. Now let's think about some intuition why this would be the case. Okay. So in particular, like what goes wrong with least squares, and why can it be so ill-conditioned? Well, if these boards were a foot lower, I would be able to explain it more quickly, but that's okay. So let's think about the columns of A. Like in particular, let's say that A has 2 columns, A1 and A2. Okay? And hopefully by now we're starting to get some intuition for like what can go wrong in conditioning. Like generically, things seem to go wrong when 2 vectors are like roughly copies of one another. Like in this extreme case, if A1 is equal to A2, our matrix isn't even invertible. Yeah? All right, so what is our picture really? I mean, there's so many different ways to talk about conditioning. So let's say that I'm trying to solve, the best approximation of B in the span of A1 and A2, right? That's what least squares is trying to do. So you give you some point here. There's B. Fun fact. Now, let's think about this picture and why it can lead to some really weird instability. Now, if I shift B up the tiniest bit, notice that it's like roughly a multiple of A2. Yeah? If I shift B down the tiniest bit, it's roughly a multiple of A1. Right? So there's 2 different solutions to my least squares problem that look very close to one another, right? 1, 0 and 0, 1. Yeah? And that's exactly the kind of case that's ill-conditioned. In fact, just to make life even worse, so here's B again. Let's say the B is somewhere in between, right? So essentially we have 2 possible solutions to our problem. Let me give you a third, which is as follows. I walk, let me see if I can do this right. Drawing is hard. Yeah, I walk really far along A1, and then I walk really, really, really far along A2, and then I get back to B. Something like that. Now, obviously, this picture is wrong because I managed to flip the direction of A2. But hopefully you guys get the point here that, like, essentially, this is the kind of thing that goes wrong in least squares problem, is that there's like this whole span of things that I can do that are all sort of very similar to one another. And from perspective of conditioning, that's a big issue because essentially there's a lot of things that achieve low error, Remember that conditioning has to do with ratio to forward to backward error, right? So like backward error is how well I approximated B, forward error is how well I got those two weights. And clearly there's a lot of different forward errors that can correspond to very small backward error, which is a problem. Okay? So this is what goes wrong with least squares, that essentially this is very common, right? You end up with columns, data points. Like for example, to use the language of data science, like maybe I have confounding factors that explain my data set, you know, like two things that kind of explain my data equally well, then like this is the kind of thing that can cause ill conditioning in the least squares problem. In big data, machine learning, all that good stuff. Cool? All right. On the other hand, I'm going to erase this picture because it's shameful. The textbook, by the way, has a version where I actually engineered it to be correct. It's hard to draw on the board. Let's think about a slightly different question. When are least squares problems really easy? Okay, what is the world's easiest linear system to solve? Let's start there. Thank you. Yeah, see, I don't ask hard questions. Right. I times x equals b. Anybody want to venture the solution to this linear system of equations? Like a really smart MIT kid that can do it in their head? Thank you, Madeline. Put me out of my misery here. That's right. So here's the solution right there. Okay. So like an interesting question you might ask is like, how close can I get to this situation in the least squares problem, right? Now remember, in least squares, the A that I solve is not the A that I'm going to invert, right? Remember, it's A transpose A. Yeah. So when are least squares problems easy? It's not necessarily when the left-hand side is the identity matrix. Then it's orthonormal. Or to translate it to this thing, if A transpose A equals identity matrix, then I actually kind of secretly have the world's easiest least squares problem. Right? Now, yeah, we have this new class of matrices, orthogonal matrices, sitting here. These are matrices that satisfy this particular property. By the way, in our brain, we often think of these like rotations, but I want to be 100% clear. A does not have to be square. Right? So these are matrices whose columns are orthonormal to one another. It actually says very little about the rows, okay? So in particular, this does not imply that A transpose equals anything at all. We don't know that yet. And when it's square, that's different, but oftentimes these matrices are not square, okay? So essentially, if you ask the sort of opposite question, like when is A transpose A well conditioned? Well, to translate it to the language that we know and love from our previous lecture, the condition number of the identity matrix is 1. It's, again, very easy to show that at least in the 2 norm. So in particular, it's somehow desirable when A transpose A is equal to identity. And in particular, I want to be absolutely clear that that does not imply that A is equal to identity. Cool? We're starting easy today. Yeah?
But if I have A such that like condition number of A is not 1, and
Yeah.
you say, okay, but I now have A transpose A equals the identity, so then condition number of C would go back to 1 here?
I'm going to let you think about whether that's possible. Okay. Yeah. Okay. So let's kind of dig into that condition a little bit more. So in particular, we've got a matrix Q, which satisfies this condition. By the way, Q is going to be our notation today for matrix that satisfies this thing, right? And remember that our previous lecture, like a couple lectures ago, we justified one of many formulas for matrix multiplication, depending how you kind of parenthesize your adds, subtracts, multiplies, which is this thing that I'm showing you in this screen. So here, the columns of big Q are going to be little q1 through little qn. So if I transpose my matrix, I just do that to my matrix. So now all the columns become rows. And now we do our like favorite little like rude hand gesture to figure out that the elements of Q transpose Q are just the dot products between all the assorted columns of Q. Yeah? So from that perspective, if Q transpose Q equals the identity, what does that imply about the columns of Q? Well, in particular, down the diagonal, it shows that all the columns have norm 1. And from off the diagonal, it shows that each of the columns is orthogonal to each of the others. Right? So that's really what that condition is telling us. Okay. Right, so that's basically all that's going on here. And that's what we're going to call an orthogonal matrix, which is a set of matrices where the columns have norm 1 and each of the 2 columns have dot product 0. Okay? By the way, I'm noticing on my slide I don't have the 2 norm. In today's lecture, our norms are 2 norms. Okay. Right. So in particular, like there's so many different ways to think about orthogonal matrices. I think the sort of simplest thing that we can do just think about it geometrically. So in particular, let's say that I take two vectors, I apply Q to them, and then I take their dot product, right? So like I have QX dot product with QY, right? We're going to use our favorite little identity that dot product is the same as transpose, like that, right? So this is really X transpose QY. This is the identity. So basically, I showed that orthogonal matrices are just things that preserve dot products, right? And in particular, if I plug in X equals Y here, then it preserves lengths. Yeah. So in some sense, Q is a very nice geometric object, right? It's just a thing that can preserve angles and lengths. Okay. Now, on your homework, by the way, I ask you guys to prove something that feels really obvious, and actually, I really struggled to write it down, which is as follows. Let's say that I have a map of Rn. In fact, I think to make it easier on your homework, I might have said R3, that preserves distances between points. So it's an isometry of R3. Essentially, what you want to show is that it's equal to an orthogonal matrix plus a translation, right? Notice that distances are not lengths and angles. They're slightly more general than that. Writing a proof of that is not hard, but it feels a little bit tautological. And actually, like writing it carefully is shockingly difficult. So I would encourage you to get started on that homework problem because it's one of these like kind of subtle ones. I can tell you that our TAs this year didn't give me a hard time because I'm guessing they didn't look closely. But the TA last year, or the last time I taught this class, I gave him the problems without the solutions. Like I think when you read the solution, you say, okay, this isn't so bad. He actually tried it and got really stuck and then told me I needed to remove it. And I didn't because I'm a jerk. So anyway, get started with that problem because it's just one of these things that really tests your understanding of linear algebra in a way that I think it requires you to kind of unravel a bunch of formulas. Okay. In any event, these Q maps are isometric. They have lots of nice properties. We usually think of them as sort of rotations or flips. You have to be careful. There's also flips in there. So in particular, what is the determinant of Q? Yeah.
1 or -1.
That's right, plus or minus 1. So it can flip things backward. In fact, what we're going to find for our QR factorization is we can choose the determinant of Q easily enough. And the different algorithms give you different determinants, which is frustrating. On the other hand, like a generic Q might do something like stretch or shear or all those other pictures you've drawn a billion times in linear algebra class. Cool? Okay. Right, so, oh, okay. I'm sorry. Cool, so now we're gonna kind of dig in and start actually deriving our new matrix factorization, which is going to be useful specifically for least squares problems. I mean, so far, I would say like Cholesky, it was kind of like a happy accident, to quote Bob Ross, that like our linear system was actually useful for least squares, or our algorithm rather. But now we're going to say like, let's say the problem that we care about from like step 1 is least squares. How will we go about engineering an algorithm to do that? Okay, and in particular, I think we're going to introduce yet another interpretation to our least squares problem, which is as follows. I mean, so far, when we talked about least squares a couple weeks ago, what did we do? We kind of said that, well, we've got a bunch of like dot products of X against the rows of A, and now we're trying to basically reconstruct X from all those dot products. Remember, that was our intuition? So that was like a very row-coded interpretation of least squares. Let's think about the column version of the same story. So what is A times X? If I think of let me write some things. Sorry, I'm like throwing my arms around, getting all excited because these are fun problems. Let's think about our matrix A. And now, rather than when we wrote down least squares last time, we wrote a bunch of rows. Let's instead write a bunch of columns, like A1, A2, so on, like that, right? Then what is AX? Well, if we kind of unravel the formula for matrix multiplication, it's a bunch of like xi, so these are like scalars now, right? Because of the elements of x times ai, which are like vectors. Yeah? So this leads us to a very familiar notion from college linear algebra class, which is like the space of all things that I can get a times x, where x is in our, I think n. We do these m by n, I think. What is this thing called? It's like not a super clever name. I know you all know, and you're just making me suffer. Alice, what is this object called? Column space. See, she knew and she didn't speak up. Kills me. I get to do that with my own students. I don't do that to others. Okay. Right. So this is the column space of A. Okay. And so here's the kind of yet another schematic for least squares is you've got this like little plane which is formed by the columns of A, right? Think of this as a two-dimensional plane. Sadly for us, the board is two-dimensional, so pictures are hard to draw. If you think this is bad, take my differential geometry class, and then it gets really bad. You have some point B, which is sitting outside of that plane, right? And my job here is to find that projection of B into this little plane, right? This is the sort of column space version of the least squares story. So from this perspective, we can think of least squares as actually kind of outputting one of two different desirable objects. In particular, there's X, which is the set of weights of the columns. But then in other times, the thing that I actually care about is A times X, which is the actual projection. Do you see that? Those are different objects. Like this point here, this is AX in our picture. Notice, by the way, let's say that I like take A1 and A2, and I want to make my least squares problem really ill-conditioned. Like I start taking those columns and squishing them really close to each other, but I leave them in the same plane. Does the projection actually change that much? You see what I'm saying? So if I like wiggle around A1 and A2, I think what we motivated at the beginning of lecture is that like the X changes a lot, right? That like this is an ill-conditioned problem. However, AX actually really doesn't change at all. Yeah? So stability of this problem and stability of finding X are actually kind of separate. Does that make sense? In particular, this kind of suggests an interesting strategy for solving this problem. Let's say that all I really cared about was this object, like the projection, which is very common, by the way. That comes up a lot. Notice if I mess with the columns of A, that's perfectly fine. So to give you a hint, let's say that I took A2 and I said, oh, I'm just going to project out the component of A2 in the A1 direction because A1's already kind of got that covered. Yeah, I can like do those kind of operations on the A's and leave this projection alone, right? As long as the span remains the same. I'm like dredging up all those annoying linear algebra words that you remember from years ago, probably haven't used in like a sentence in a long time. Does that story make sense? That's going to be our schematic for today, is what we're going to do is mess with the A's in a way that improves the conditioning of the A matrix, but doesn't mess with their span. Cool? Cool. I think this is fun. So in order to do that, we are going to prove a quick lemma, which is in my notes somewhere. Which is as follows. Like, remember our strategy from Gaussian elimination. We started with a matrix and we started like pre-multiplying by all these like forward, backward substitution things. So what we're going to do now is invent a new matrix which takes columns of A and messes with them, right? And our goal being to eventually lead to a very well-conditioned matrix. So, spoiler alert. First of all, if I want to mess with columns of A, do I pre or post multiply by elimination matrices? Which one of those two things actually make columns? Yeah, post, right? So far we've done row operations, so those are kind of on the left. Now I'm going to take A, and I'm going to start post multiplying by a bunch of matrices, like a bunch of elimination matrices, E1 to EK. And remember, our goal is going to be to lead to some matrix which is really, really well conditioned for least squares problem. So what do you think is going to be my goal? Like, what do I want this product to be? What would make least squares problem super well conditioned? Yeah. If it's an orthonormal matrix, right? So this is going to be our strategy, is to come up with a sequence of E's that I post multiply A by that eventually lead to a Q with orthonormal columns. Okay? Now let's say that all of these guys are upper triangular, UT for University of Texas. Okay? I can remember the product of upper triangular matrices is itself upper triangular. So I can move that over here, and now I'm going to get, spoiler alert, this factorization, where Q is this orthogonal guy, and then R is going to be like basically all these upper triangular matrices. I haven't told you how we're going to do it yet, but that's going to be our goal. Does that make sense? And in fact, let's say we want to solve the least squares problem. because we do. I mean, you're in this class, so like you don't have a choice. Okay, so in particular, we have A transpose A x equals A transpose B. Everybody on 3. What's the name of this linear system equations? 1, 2, 3. Okay, so what is A transpose A in this particular case? So it's R transpose Q R. What's Q transpose Q? I. So in particular, this is R transpose Rx equals A transpose B. So this is going to be R transpose Q transpose B. Everybody agree with me? Now, so far I haven't really done anything from perspective of conditioning. Like the condition number of this is actually the same as the condition number of A. I'll let you convince yourself that's true in the 2 norm at least. However, here's the thing that I can do, and I want to be absolutely clear. We're doing this theoretically and not algorithmically. Okay? This is going to be really critical because if I do this algorithmically, I would induce numerical error. But theoretically, if this system is true, and if R happens to be square and invertible, which it is because it's a big product of elimination matrices, then I can just multiply both sides by R transpose inverse. And now I have Rx equals Q transpose B. I want to be absolutely clear. The step that I just did here is a theoretical step. It is not an algorithm. Does that make sense? Like basically, if I solve this, then I've solved that and vice versa. Cool? You're all kind of nodding, but I noticed that like the radius, the nod radius has shrunk, so that makes me nervous. Okay.
Why is RT invertible?
Because these are all going to be elimination matrices. So that's going to be, yeah, we're going to construct it in a minute to be invertible. But for now, like you can trust me. I'm very trustworthy. Okay. Here's the cool thing. Condition number of R looks like the condition number of A. Yeah? So if I solve my least squares problem in this sense, I don't induce that squared condition number problem we had before. Isn't that sneaky? This is super cool. You guys don't look excited, but this is a really cool idea. Like whoever came up with this, I don't know, probably Graham or Schmidt. Like they're really smart dudes. Like this is a clever idea. Moreover, what is the time complexity of solving this linear system of equations? Your mouth on the answer. Right? Wait, raise your hand. Help me out. What's the answer? That's right. This is a quadratic system of equations to solve. Or, sorry, that was a poor phrasing. This takes quadratic time because R is upper triangular. So we get all of our benefits in one. Okay? However, how much storage does it take? Well, now it's like slightly more than quadratic. I mean, it's still quadratic asymptotically, but notice that like Q is no longer triangular, so I got to store everything. Yeah. So like you do give up a little bit relative to LU. Okay. So that's our story. So now we just have to fill in the details, which is good because as always, I've talked too much and I'm running out of time. Okay. So here's what we're going to do. We're first going to prove a lemma, which I think we all kind of know spiritually. Which is to say that like this kind of thing is well justified. Namely, if I post multiply A by an invertible matrix, I don't mess with its column space. Right? So more formally, that proposition is stated on the screen here. Is it okay if I erase this so I can keep writing? Cool. It'd be really fun if someday I got a classroom in the building where I work, which has these screens above the boards, but this is cool too. Okay, so in particular, we're going to prove a little lemma. This is the kind of lemma that I think like you prove a lot of in undergrad like math class just to basically get you used to writing proofs. But essentially, here's our claim, which is as follows. For any A, which is in R m by n, notice here I'm not requiring A to be square. That's going to be true throughout today's lecture. And invertible B, now B is invertible, so it's got to be square, right? So in particular, it's n by n. We have that the column space of A is equal to the column space of A, B. Okay? Now, I think whenever you're asked to prove a lemma like this, you could think really hard, or you can just do the kind of like Toucan Sam style, like follow your nose approach, right? Like just take a thing in one space, find that it's in the other, do the opposite. Yeah? So, what direction do I want to go first? This is just like a choose your own adventure. Yeah. A to A, B. Fabulous. Okay. 1. Take I have notes only because, as you guys have figured out, I confuse myself with like letters all the time, which is a problem when you teach math. Okay, so let's say that I take B, which is in the column of A, like that. Then by definition, there exists an X, oops, there's an X, so that AX is equal to B, like that. Right? And remember that we're trying to show that B is also in the column space of AB. So one thing that I can do is just kind of like wedge in here B times B inverse, right? Because that's the identity matrix. Okay, so in particular, we have shown AB times B inverse X, which is just some other matrix vector. We could just like call it Y is equal to B. So in particular, AB times something is equal to this other guy, and hence B is in column space of A, B, like that. This is not a tricky proof. Cool? I'm a little low on time. Is it okay if I leave as an exercise to the reader doing the proof in the other direction? We're all adults here, yeah? Okay, cool. All right. Right, so that's our basic point, which is that essentially what we're going to do is we're going to start with our matrix A, and we're going to just keep applying B's and see if we can get, how close we can get to orthogonal. Okay, so that's our strategy here. So in particular, that's going to lead to this factorization that we've talked about, and as I already justified because I forgot what was in my slides, this gives us a nice, well-conditioned way to solve least squares problems by doing QR factorization and then solving another system. Notice that this is like not AX equals B or A transpose AX equals A transpose B, but some third thing, and that this third thing is actually pretty well-conditioned to solve and is pretty efficient. So, okay. Notice we never needed to compute the Gram matrix or its inverse. Okay. So now all we have to do is like actually carry out this, this algorithm, okay? So in particular, what we can do is just revisit an algorithm that I'm guessing you already know from linear algebra class and show that it actually does exactly what you want. So remember in linear algebra class, I feel like in linear algebra class, they often forget that like what you're doing is useful. But essentially, I think the first thing you do is learn how to solve linear systems using Gram-Schmidt. The next thing you do is you learn how to orthonormalize. You learn to take a set of vectors and then come up with an equivalent orthonormal basis, yeah? And what algorithm do you use for that? Anybody remember? Like, I think all linear algebra classes teach the same thing. It rhymes with something? Yeah. Gram-Schmidt orthogonalization. Gram-Schmidt is really, really simple. You have a set of vectors, and you're trying to come up with a different set of vectors that spans the same space, right? What do you do in Gram-Schmidt? Well, the first thing you do is you take your first vector and you just divide it by its length. And essentially what you're doing kind of inductively is building up a basis one vector at a time, right? So you're going to add the next thing to your set of vectors and project out all the previous stuff, and then divide that thing by its length. Then add the next thing to a set of vectors, project it, divide, and so on. Yes? So one thing that I'll let you justify at home, because we're a little low on time, this is a good question, because I guess I didn't answer that explicitly, is that the condition number of R looks like the condition number of A, not of A transpose A. And that's because you got R by starting with A and multiplying by a bunch of orthogonal matrices, which don't affect the condition number. Good question. Yeah. Okay. So in order to do that, to derive this Gram-Schmidt algorithm in a little more detail, we need to talk about what it means to project. I think this is often a thing that you see as a formula in algebra class, but maybe didn't justify carefully. So we'll spend a minute doing that. So in particular, we'll start by easy stuff, which is just projecting one vector onto another. Which is to say, we want to find the closest multiple of vector A to another vector B, okay? So if you think about it, this problem is really a scalar problem, right? Like essentially, we're just scaling A up and down to be as close to B as possible. So this is a least squares problem if we want to have like the grand unified theory of least squares. And it looks like this, but now my unknown is just a scalar C. So rather than thinking too hard, I think a thing we can do is just take this norm and expand it, yeah? So in particular, hopefully we're getting sick and tired of this calculation by now. If so, I've done my job. Then we have minus 2 C A dot B plus mod b squared, like that. Yeah? Now, what's my unknown here? C, right? So this is just a one-dimensional optimization problem. So either you can take derivative with respect to C, set it equal to 0, all that good stuff, or if you remember your high school algebra class, there's actually a formula. This is like the vertex of a parabola. And what you're going to get, hopefully it's okay if I just write it. I think at this point we've done this calculation in like 18,000 different forms, is that C is equal to A transpose B, like the dot product between A and B, divided by mod A squared. Cool? I'm happy to do that calculation if you don't trust me. She trusts me. That's great. Okay. So in particular, the projection, this is basically just to give you a little notation, onto A of B is going to be equal to C times A, which is A transpose B over mod A squared times A, like that. Cool? By the way, just because it's going to be convenient for us later, notice that this, if we're being really pedantic, is like a 1-by-1 matrix, right? And A is like an n-by-1. So in this form, it actually kind of doesn't parse if I want to think of this as a matrix expression. This is like totally pedantic thing because we all know that that's a scalar, so it's like kind of okay. But I think a very typical thing is to put the A over here. The reason that I'm going to do that is you can reparenthesize a little bit. And notice this gives you a different expression, which is A transpose, all of that times B over A squared, right? So do you guys see that there's just like a lot of different ways to write the same thing here? Cool? By the way, notice that there's like kind of an A squared there. So it's kind of like taking both of these A's and dividing it by its norm. Yeah? So from this perspective, you can kind of see what's going on. By the way, it's a B, I'm sorry. This is just projecting B onto A, right? So this is like dot product between A and the normalized A and B, and then putting it onto A. Cool? A lot of ways to reshape the same boring formula. Okay, and by the way, so we always draw the same picture, right? Like that this somehow is orthogonal to the other piece. So let's double check that really quick. So notice that A dot product with everything that's left, so B minus projection onto A of B. Well, if we expand that, we have we've got A dot B minus A dot this thing, right? So notice that that's A transpose B divided by mod A squared times A dot A, which is norm of A squared like that, right? These two cancel, right? And then you have A dot B minus A dot B. This is 0. So that kind of just verifies that the picture that we always draw is correct. Okay, nothing too exciting so far. Okay, right, so that's our formulas so far. Any questions? This is just rederiving undergrad linear algebra, nothing too exciting. Yeah. Mm-hmm. That's right. Yeah, so that's a good question. So the question was like, why the heck did I do this? And I think this is a very common trick in machine learning, so it's kind of worth getting used to thinking about it, which is like in linear algebra, you think of this thing as a scalar and then you kind of never go back. But you can also think of it like a 1-by-1 matrix. And from that perspective, this product really doesn't parse, right? Because you shouldn't multiply a 1-by-1 by an n-by-1, right? And so from that perspective, putting it kind of swapping the order of these two guys is sort of the like morally correct thing to do. It's awfully pedantic, but that's right. And the idea here, all I did was reparenthesize that expression. What is this matrix up to scaling A? This is just the matrix that acts on B and gives you back the projection of B onto A. Yeah. This is kind of nice. This is going to happen a lot. Like, by the way, so the math trick that's all the rage in stochastic gradient descent right now is this Hutchinson trace estimator. And it's basically another version of math that really depends on thinking about this kind of expression carefully. And then you put a trace on the outside and you start cycling it around. We're going to use similar tricks in a couple weeks. Cool. Right, so essentially we've shown a bunch of properties, that the projection of A onto B is parallel to A by definition, and moreover, what's left is perpendicular. Cool? All right. Moreover, let's say that we have a bunch of orthonormal vectors. We can expand our formula ever so slightly. So if they're orthonormal, they, in particular, have length 1, so this term goes away. I don't have to divide by length anymore. And the one thing that we haven't shown is a slightly more generic version of our least squares problem. We're not going to do it because I don't want to, and I'm the guy talking, which is as follows. Right, I could solve the following, which you might recognize as basically the least squares problem in disguise. The sum of AI hat times Ci minus B squared, right? So this is just a more generic version of the problem we wrote up there. Now we have a bunch of A's. Now normally this is just least squares, but if we additionally make the assumption that these are orthonormal vectors, then essentially what's going to happen when we expand out the square here, in fact it's on the slide, so that's good enough, is that all the cross terms are going to go away, right? Because they're going to be like AI dot product with AI, AJ. So you get a bunch of copies of the problem that we solved on the top. And essentially what we get is that every one of our projections is just dot product. I kind of rushed through that. Is everybody okay with these formulas? I think they're familiar. I'm just dredging up old stuff. Cool. All right, so that leads to a slightly more generic formula, which is to say if I have the projection of B onto the span of A1 through AK, so long as they're orthonormal, notice I've put these cute little hats there, which is telling you they're orthonormal, then it's a very straightforward formula. Okay. So here's our strategy for orthogonalizing a set of vectors, which you might have forgotten was our goal, which is as follows. We're going to take V1 and just divide it by its length, and that's going to give us the first vector in our set. Now we're going to take the second one, project out the first one, divide it by its length, that gives us the second vector in our set, and so on, right? So we can just do that recursively, and that's called the Gram-Schmidt algorithm. Here's some pseudocode. Cool. I think this is pretty straightforward. And it's like essentially something that follows from the little lemma that we proved about column spaces is that the span of the V1 through Vi, kind of inductively for each I, is equal to the span of the hat A's, right? Essentially, when I projected stuff out, I didn't mess with the span. And that's what sort of justifies this algorithm, right? So by the time it finishes, what it gives us is an orthonormal set. I'm rushing a little bit because this is the boring stuff, but if you have questions, you should stop me. Okay. So here's the thing, like remember what we did when we talked about Gaussian elimination? We kind of did the like college linear algebra thing, and then we stepped back 50 feet and we realized that this led us to a matrix factorization. Notice that exactly the same thing happens here, right? So in particular, well, what are my two operations, right? So let's say that I implemented this algorithm in the columns of a matrix. Literally, I just have on my computer an A, which I start out, I guess, as V1 to Vn, right? And then the first thing I do is just divide this by its norm. It gives me A1, then projection, A2, A3, so on, yeah? Okay, dividing a column by its norm is like post-multiplying by a matrix of the form 1, 1, 1, 1 over the norm of Vi, and then a bunch more ones, yeah? So clearly we've shown that 2.1, or I guess the denominator of 2.2 rather, is sort of an okay thing to implement with an upper triangular matrix, right? Diagonal things are upper triangular. Cool so far? The one that's a little harder to think about, I'm gonna let you think about it at home because this is actually not the algorithm people use, is what is the other thing I have to do? I take a column, I look at a previous column, I project onto it, and I subtract it out. If you think about it, there's an upper triangular structure hiding there, right? Because I never look forward. I only look at the previous columns, yeah? So what you're going to be able to convince yourself, this is not entirely obvious. Like if you just write the formula, you can kind of factor it the way and you'll see, is that you'll end up with a matrix that looks like the following. A bunch of ones down the diagonal, because I haven't messed with anything. And then a single number here, which is like the amount of the previous guy that I'm going to project out and subtract. Cool? So if I multiply all those guys together, I get an upper triangular thing. And that's what leads me to my QR factorization. That essentially my high-level point, and I'm rushing because, again, to repeat, and we'll say why in a second. This is not how people actually implement QR in practice. so I don't think it's worth like deriving these in great detail. I just want to convince you that like the algorithm that you have done by hand a bunch of times in linear algebra class actually does translate to a matrix factorization. And in fact, by the way, like kind of a thing that your linear algebra teacher should have done and probably didn't. Let's say that like I didn't realize all this and I didn't know anything about elimination matrices. So I just took an A and I started eliminating its columns until I got Q. I could certainly do that, yeah? Notice if A is equal to QR, remember that Q transpose Q is equal to identity. So in particular, R is equal to Q transpose A, yeah? So here's a lazy implementation of QR, which is to completely forget about R. Just do Gram-Schmidt on the columns of A, and then just pre-multiply A by Q transpose, and presto changeo, what you'll find is you got an upper triangular thing. It's kind of like one of these things that's like a little bit magical because you might not have really thought about it that way, but just by definition of Q, that has to be the case. Does that make sense? Sneaky. This is like the lazy man's implementation. Yeah.
Significantly slower.
No. Yeah, that's a QR is cubic time algorithm. That's actually perfectly fine. Yeah, I think it's slightly worse because essentially like you just don't need that last step if you just kept track of Q, but it's insignificant in the scheme of things, unless you're one of these hardware guys that cares about constant factor. Cool. So at the end of the day, essentially what we've sort of justified is this factorization QR, and we've already talked about how we can use it. Now, one question, I keep saying Gram-Schmidt is not a terribly good idea from a numerical perspective, but I haven't said why. Here's why. So let's say that my columns of A are nearly linearly dependent, meaning that they're like nearly parallel to one another. So think about what QR does. It like takes a vector, it projects it onto the other guy, and it divides by its norm. So hopefully this picture actually suggests where things go wrong numerically. Remember that like anytime we're dividing by small numbers, things tend to go wrong. I think your last homework kind of drove that point home. So take a look. The two columns of A here are actually not small numbers. They're like big vectors. But the projection of one onto the other gives a relatively small object that then I amplify by dividing by its norm. And it's that operation which is very imprecise. Yeah? So if you want QR to go wrong, like code up Gram-Schmidt for fun and use these two vectors here. Notice that they're nearly parallel. I just took the second element and scooted it around a bit. And you'll see that your code like divides by a really small number really fast. Does that make sense? Cool. So what are we going to do? Come up with a new algorithm for QR factorization that doesn't do this, yeah? And in particular, again, I think that the thing to just keep in mind when we talk about QR is that there's at least one object which is always well conditioned, and that's the Q part, right? And so like sort of, I think the bias here is to say, what can I do to construct an algorithm out of rotations and flips rather than out of elimination operations to carry out the same thing, right? At least from a high level, you might be able to understand that like that's sort of a good strategy here. So in particular, so far, we've done the following, which is to post-multiply by upper triangular matrices until I get a Q. Anybody have an idea from like 50 feet away what's going to be my next strategy? Let's think for a second. I'm going to start again with a matrix. I think we can erase this proof. It's not the world's most insightful thing. Okay. By the way, in case you guys haven't figured this out, I feel like there's always at least one kid in this class that like just doesn't bother opening the website. All of these proofs are in the textbook. This is like, we're following it pretty closely. Okay. So, right, so previously we did this, and then we started multiplying by a bunch of elimination matrices until we got Q. Yeah. That's right. Yeah. So instead, I'm going to start doing elimination matrices like this until I get R. Okay. So in that case, what set of things are the E's going to have to be in? Not lower triangular. We're not trying to get Cholesky anymore. Orthonormal. Remember, in the first strategy, these were all upper triangular to get a Q. Now these are going to be orthonormal, right? So in particular, let's call this Q transpose, maybe. And now, if I pre-multiply by Q, then I get QR, right? So in some sense, what we want is to do some version of forward elimination, right? Just like in Gaussian elimination, right? That would be ideal, right? Is to basically just re-implement Gaussian elimination, but somehow instead of using forward substitution things, which are triangular, use orthogonal matrices. It's not obvious how to do that, but like that like in a world where we had our, you know, glitter and rainbows and elimination matrices, that's probably what we want to do. Does that make sense? Okay, so that is our goal for the remainder of lecture here, is to derive a second strategy where you pre-multiply by orthogonal matrices to get R, as opposed to post-multiplying by triangular matrices to get Q. For the rest of this week, every morning when you wake up while you're brushing your teeth, I want you to say that phrase with your mouth like wide open so that the toothpaste goes everywhere. Cool? All right. Now, here's the kind of thing that I think we should think about a bit. So when we derived Cholesky and when we derived LU, we talked about these elimination matrices, and in some sense, like, they're just convenience objects. Do you see that? Like, they're just kind of like algebra implementations of an algorithm. There's like nothing special about these things. I mean, there are, like, they're triangular, but like it's somehow like, for instance, like the elimination matrices we saw in LU really had nothing to do with like where my algebra problem came from, right? They're just kind of these things that were useful, yeah? And like in particular, like they also don't span the set of all possible matrices. They're like these specially designed forward substitution matrices were just enough to carry out LU, right? So now from like a design perspective, right? Like if I'm playing designer, one thing I might do is kind of go back and say, okay, so now I got to design elimination matrices from some class of matrices that are easy to work with that satisfy the criteria I want. Like I no longer care about triangularism. I don't know. I don't care if my matrices are triangular anymore. I want them to be orthogonal. So one thing I might do is like open up my big grab bag of orthogonal matrices and ask like, what are ones that are kind of easy to work with? Yeah, and I've already given you guys a picture of like two classes of orthogonal matrices that kind of feel okay. Yeah, you remember what they are? Yeah, rotations and like flips, like reflections. And in fact, if you look at the major classes of QR factorization algorithms, there's one that uses rotations, and there's one that uses reflections. Yeah. So in this class, we're going to derive the reflection-based algorithm. Under homework, I don't think we have you derive the rotation-based one. We did 1 year when I taught this. And it turns out that they're both like roughly equivalent. The rotation one tends to work better for sparse matrices because you kind of target one element at a time. The flip-based one is a little bit better for dense stuff because you're going to just like annihilate one column at a time. But from a time complexity perspective, they're actually the same. Okay. So the thing we're going to cover, it's actually interesting, like for whatever reason, the names of the people that these algorithms are named after are like, they sound like English words, both of them. We're going to cover the householder algorithm, which is named after Mr. Householder. I don't remember anything about him. The other algorithm, if you want to look it up, is called Givens rotations. And essentially, it's going to like use a bunch of cosines and sines and be like rotating things. Yes? That is a good question. The answer is no, actually, because what we're going to do in this algorithm is really sneaky. We're going to do each, so remember our kind of football diagram of Gaussian elimination where we kind of annihilate one column at a time? We're going to show that we actually can just do that with one reflection per column. But that reflection matrix is going to be dense. It's going to be a big guy. What happens in Givens rotation is you do kind of one forward substitution at a time. So you end up with like a little block 2 by 2 guy. Yeah. Question or itch? Itch. Okay. So here's the object we're going to define. We're going to define one particular kind of fun matrix to work with, which is going to take in two vectors, b and v. And what we're going to look for is the reflection of b over v. Okay? We're going to give this matrix a name h sub v. Actually, to be precise, we're going to call it minus h sub v because we like orientation preserving things. Okay? So we're going to do this first kind of algebraically, and then we're going to show, actually, to go back to our question earlier, that we can just basically refactor our expression and then get a matrix rather than like just a big ugly expression. Okay? By the way, notice that this is not like a full set of operations on vectors. In particular, this is happening in the b comma v plane. We're going to assume everything outside of that plane is just kind of left alone. Okay? So in particular, here's the picture we're going to draw. It's always really annoying to draw these things for me because I'm old. Okay, so here's v. Okay, And then here's some other vector b. Okay? So we're going to do this kind of pictorially, and then we're going to derive a formula. So remember that I can take b, and I can decompose it into a part that is parallel to v and a part that's orthogonal. So if we care about reflections, we actually care about the orthogonal part. So what is that vector there? Well, okay, let's start with this point. So that point there, this is going to be the projection onto v of b, right? So then this vector here is going to be projection onto v of b minus b. Does everybody agree with me so far? So then to reflect over, you're just going to add this vector a second time, like that. So we're just going to copy this guy here, and that's going to give us our reflection. Okay, so let's work out like what this thing is. Okay, so in particular, we start with b, and then we add 2. These are supposed to be the same. I've obviously drawn this very poorly. 2 times this vertical guy, right? So in particular, I'm going to have b plus 2 times the projection onto v of b minus b, like that. Everybody agree with me that this is this guy? Then we're going to factor this expression to look at matrix vector product. Okay, so in particular, if we substitute in our formulas that we know and love, we have, well, first of all, let's just simplify this guy a bit, sorry. So we have a b minus 2b. So this is really 2 times the projection onto v of b minus b. Hopefully you're with me so far. Am I with my notes? Yes. Okay. So now we're going to plug in our expression for this guy. This is going to be 2v transpose b over v transpose v minus b. Notice that I'm using the version of this expression that kind of parses from a matrix multiply perspective. Okay? And why do I do that? Well, remember that essentially my goal here is to view this as an action on b. So I'm going to factor this out as a matrix vector product, which looks like something times b. Does that make sense? And notice I can kind of do that. I've got a b here and a b there. So I can write this in a fun way. There's this like cafe in Davis Square that always labels everything fun drinks. Okay, so this is 2v transpose divided by v transpose b minus identity times b. Cool? See what we did there? It's kind of sneaky, right? We started with like a vector thing, and we just kind of parenthesized it, and suddenly a matrix came out. Isn't that kind of cool? So we're going to give this guy a name. Annoyingly, when I wrote this book, I had to go back and change a bunch of signs that introduced a billion typos. This thing is actually minus hv. Notice that like if a matrix is orthogonal, then so is its minus. Yeah. Now, if you're curious, the historical reason for this is that we're going to use a bunch of these guys to do Gaussian elimination, or like some version of Gaussian elimination. If I keep pre-multiplying by this without the minus sign, our algorithm is still going to work, it turns out. Like some of the details will have to change. But the problem is the determinant is going to keep flipping back and forth between plus and minus 1 of q. Whereas if we use this guy, it'll just stay plus 1, which is kind of nice. Because, for example, the Givens rotation algorithm is always a positively oriented thing. For this class, it's not going to matter a whole lot. In certain corners of physics where like that kind of stuff matters, like conveniently Sina, our postdoc, is in the room, who works on a lot of stuff where like the determinant of q is like absolutely critical, then you might as well use an algorithm that like has that additional guarantee. Okay. So essentially, our goal here is going to be to do something like Gaussian elimination, but every time we used to have a forward substitution matrix, our question is whether we can instead use a matrix of the form HV, right? Notice this guy is no longer triangular, but it is orthogonal. Well, actually, I guess we didn't prove that, but I'll let you check that at home. Like pictorially, I think it's pretty clear that it's orthogonal. Okay. Oh, immediately, I also put in the slides the math we just did on the board, and hopefully, yes, we agree. Fabulous. Okay. So let's think a little bit about our sort of football diagram style linear algebra here, right? So we start out with some generic matrix A that we know nothing about. In this case, by the way, division by 0 is going to be a little bit less critical, which is interesting, because remember in forward substitution before we had to worry about pivoting, that's actually going to turn out to be irrelevant here. So let's say that I have some generic matrix And remember, we're just kind of using these x's as like placeholders for like, I don't know what's, I don't know what number is there. Right? Remember, my goal is to do a bunch of operations on this until I get something upper triangular. Yeah? So what would I like? I would like to multiply this by some matrix of the form HV so that I get, in our first step, this is kind of cool. Like, remember in Gaussian elimination, we kind of do it one row at a time. We're going to be greedy. We're going to say, I want to get some number. I'm going to call it C. I'm not going to be so worried about the diagonal because we can kind of fix that later. And then a bunch of zeros. And then I don't care what for the rest of this matrix. That's my goal. Does that make sense? And then what we're going to do is just kind of like do this inductively, like do it one kind of block at a time. So here's what we're going to do, which is kind of sneaky. I don't love this proof because like I feel like it's nice when everything is natural and follows from the thing before it. But we're going to kind of say like, which I think is kind of reasonable from an engineering perspective. Like, gosh, wouldn't it be nice if I could find a v where this were true? We're going to work out what that v would have to be by plugging it into this expression, and then show like if we kind of ran our tape in reverse, right? Like you play your audio tape the other way, you hear like satanic ritual, and then what you figure out is that actually you canceled out the first column of A. Yeah? Okay, so in particular, what do we really want? Is it okay if I erase this little picture so I have some space to write? Yeah? Cool. So let's take A to be, for now, column 1 of matrix A. Okay, like that. And then what I want, all I want, is that HV times A is equal to, remember that picture we had a C and then a bunch of zeros? So if I want to translate it to this language, I have C times the first standard basis vector. Right? That's what I'm looking for. Everybody with me? That's our design goal. I'm supposed to say design goal. That's useful in engineering. Okay. So here's what we're going to do. We're just going to plug in the form of HV and see what happens, right? It's important not to think here. So in particular, let's kind of write an equal sign this way. We have, just from before, identity minus 2 v transpose over v transpose v times A is what's equal here, okay? And now we're going to expand out this expression, and what will we get? So anybody want to tell me what is identity times A? Louder. The third time. Oh my God, the people in the back this time. Okay, there we go. All right, so this is A minus. Okay, I'm not going to make you scream out a bunch of letters. So now we have 2v times v transpose A over v transpose v. That's supposed to be v. Everybody with me so far? Okay. I don't know how you guys haven't figured out by now. Like, whenever I ask a question, the answer is always 1, 0, or the thing I just said. Okay. So in particular, notice that there is a v here, yeah? And everything else here is stuff that I know or a scalar, okay? So I can solve this expression for v, and what will I get? I will get that v is equal to A minus C times E1 times V transpose V over 2V transpose A. All I did here was algebra. You guys see that? So I have CE1 is equal to this big expression. I post-multiplied by this 1 over this constant, and I isolated V. That's the expression I got. Cool? All right. So in particular, there's this unknown thing, basically C, hiding there, right? But notice that like this actually already gave me some information. So this second object, this is just a number. Do you see that? It's just a scalar. So in particular, V is parallel to this object. Do you see that? Like from vector perspective, this is just some constant scale times something. So we actually learned a lot about V. Like if I want V to have this property, then V has to take this form up to a scale. Now, here's the next thing. Does scaling V actually affect the definition of H sub V? You can either do this algebraically or you can just think for a second. The answer is no, right? So HV is reflecting over V. If I scale V up and down, that doesn't affect the reflection, at least by a positive scale. We'll come back to the sign later. Okay, so in particular, we can do a weird thing which feels uncomfortable mathematically, but is actually fine, which is the following. We can take v to equal a minus c e1 for some unknown c. Do you see that that's fine? Because I can scale it up and down any way that I want. So I'm just going to choose the scale so that this number happens to be 1. This is called lazy math. Okay. So if I do that, one thing I can do just to make my math even more tautological, I just made this choice. I can plug it back into this expression to get a recurrence. This feels uncomfortable, but I can do that. You guys see the only kind of weird thing I did was this definition here. Yeah? And what I'm going to get, oh, in fact, actually, I'm sorry, we can plug it in to this expression here, even easier. Yeah? Okay. What is the left-hand side of this expression? Well, it's still v, like that. Okay. And now we're going to have a minus CE1 times v dot v over 2 v dot a, where now I plug in this particular expression for v into the second piece. Feels weird, but I can certainly do it. Okay, sorry, I was Give me a second. What was I doing? I had a point here and I forgot it. Oh, yeah. Okay, so this thing is a vector. This other thing is a scalar. So in particular, I can take the dot product of both sides of this expression with v. Okay, and what am I going to get? Well, on the left-hand side, I'm going to get v dot v, like that. Okay, and now I've got v dot a minus c e1, all that, times v transpose v by 2 v transpose a, like that. Cool? Notice this is kind of convenient because I got a v dot v on the left and on the right. Yeah, so now we're cooking with gas, right? Like we're getting somewhere. You can see me sweating because this proof makes me uncomfortable. Okay. So assuming for now that v is non-zero, notice that if v is 0, that kind of corresponds to like I didn't need to flip the first column of my matrix to begin with, which like I could detect before I got there. Okay, so in particular, I have 1 is equal to, well, let's see here. So we have v over 2 v transpose a. Let's think about where that expression came from for a second. I'm sorry. Oh, I'm sorry. I made a dumb, it's not a mistake. Everything I wrote is correct. It's just not where I wanted to go with this proof. I'm sorry. The last like 2.5 minutes were not wrong. They're just vacuous. I'm sorry. It's funny because every time I think like, oh, okay, I can stop in my notes and then like I'll get it from here. That's when it goes wrong. Every single time. So my sincere apologies. I'm a terrible instructor. You can take it out on me at the end of the semester. So in particular, this object is now v, right? So v is equal to v times this scale. Sorry, this is much better. I think you can get to that expression by doing a bunch of other dumb stuff, but there's no need. It's hard to think critically looking at your notes in front of a bunch of people. Okay, so v is equal to v times this scale. So what is this scale equal to, assuming v is non-zero? 1. And that's the expression I have on the upper board. So we didn't need all that heavy stuff. I'm sorry. Mea culpa. Okay. Have I lost you guys? I know the second I make a mistake, the whole class tunes everything out. Okay, so 1 is equal to v dot v divided by 2 v dot a. And now I'm going to plug in my expression for v, which is up there. Okay, and what am I going to get? I get mod a squared. I promise we're almost done and your instructor will stop sweating. Minus 2 c e1 dot a plus c squared divided by 2 mod a squared minus c e1 dot a. Everybody agree with me? Now we're back on track. My bad. Okay, so if I multiply both sides by the denominator, I do some reshuffling, all that kind of stuff, right? What am I going to get? I'll get basically the denominator and the numerator are equal to one another. Notice that like some nice things are going to happen because like you've got a 2a squared and an a squared there, right? So after I simplify, what I'm going to get is c squared is equal to the norm of a squared. Everything else cancels. Isn't that cool? My apologies for a slight misstep there. Okay, and in particular, c equals plus or minus mod a, not squared. So there's still a square root in this algorithm, by the way. It kind of looks like Cholesky that way. Okay? So we have to be careful what we've shown and what we haven't shown. Oh, and it's actually completely in my slides. I could have just followed these. Oh, my bad. Okay, so what have I shown? I've shown that if such a v exists, then it has to take this form where c is equal to plus or minus mod a. It turns out it doesn't matter which of those two you choose. Now here's what you can do. Run this whole proof in reverse. And essentially what you show is for this choice of v with that choice of c, your elimination matrix does exactly what you want. It gives you exactly this structure. Okay? So what we've shown is what's on the screen here, that if I choose HV, where v is equal to a plus or minus mod a times E1, if I pre-multiply my matrix by that thing, it will annihilate the whole column and stick a C in the front. Moreover, we know that C is the norm of A, so we can pre-multiply by a diagonal thing to get rid of that. Cool? Gosh, I'm schwitzing. Okay, so that's our basic trick. Now, what are we going to do recursively? Well, essentially, what I've really given you is a way, if you think about it, I've given you a way to take something and annihilate everything underneath it, right, by pre-multiplying by a particular matrix. So let's say that I now am at a stage kind of inductively where I have like a bunch of ones and then some block down here, right? And now I'm trying to basically deal with this column. Does that make sense? There's actually two different ways you can do this. One of them is derived in the book, and then this morning I derived a second one. We're a little low on time, so we're going to skip it. But essentially, what you can do is pre-multiply by a block matrix, which is identity, right? Which is the identity acting on this block, a 0, 0, and then an HB that acts on that block, right? So you can use exactly the same formula as we already had, just one after the next. Notice that if this is orthogonal, then very clearly this whole matrix is orthogonal. And that gives us our procedure for QR. Is that cool or what? And notice we did that completely. Basically, this is just Gaussian elimination, but every time we're going to do a forward substitution, instead we do a reflection. That's it. Yeah? The textbook, by the way, derives a slightly different way, which is basically equivalent to this, where you do it in blocks. But either one is all right. Yes?
Like in this derivation, like we still do the whole projection thing that caused the problem in the first, like in.
Not quite. Notice in this one.
Choice of B is nicer, so if two columns are close, it's actually like you pick a different vector.
Notice that this operates on the rows. It doesn't operate on the columns.
Or like even same thing.
Yeah. So there's a question which is like maybe the row space could be a little conditioned. That's absolutely right. But if you look at these formulas here, notice there's no division. Yeah. So actually, we really did overcome a lot of the issues. If you wanted the division, but where you would have to get it is the fact that technically we didn't put a 1 there, we put a C. So there is division, but at least it's sort of self-contained. Yeah. Great question. So at the end of the day, our new house order QR does a slightly different thing, right? It pre-multiplies by a bunch of H's and gives you R, whereas before we post-multiplied by a bunch of substitution matrices and got Q. Does that make sense? Isn't that cool? This is such a cool algorithm. Okay. And so essentially, by the way, this Givens rotation method, all it does is basically work through like cosine and sine of an angle to rotate 2 rows at a time. It's like the logic is exactly the same. It's just the details. Notice, by the way, there's kind of a weird way to store Q if you wanted, which is to just store the list of V's that you calculated, to go back to the question we had before. And in that case, like, you don't have access to the elements of Q, but you can still kind of work out how to multiply by Q transpose in terms of the V's pretty easily. Yeah, sneaky. So to conclude our lecture today, I want to mention one final thing. I'm sorry, I'm going like 2 minutes over. I'm so sorry. Which is just a little bit of a detail here. We began our lecture by talking about our matrices and that they're actually not square. And so I actually slid past you a slight technicality. When I did Graham-Schmidt, which things were square? Well, they were our elimination matrices, right? So if I have an n by n thing, then Q, right, which contained that orthonormal basis, stayed non-square, right? I just was doing all these substitutions, and R was a big square guy, right? And now, when I did house order, actually the opposite happened, right? Because I was pre-multiplying by a bunch of square matrices, these HVs. So the thing that remained non-square was R. So there's a reasonable question here, which is like, how do I convert from one form to another? So let's say that I did QR. So now I have like a giant Q that's square, and I have an R, which is not. R is still upper triangular, so in effect, it has some structure like this. There's like a triangle up there, and then a bunch of zeros down there. This looks like that Squid Game logo. Okay, so now, one thing that I can do is I can take Q, and I can break it up into the set of columns that act on the triangle, and the set of columns that act on the zero. Obviously, this is the same as Q1 times, if we call this like R1, R1, right? So there's a very easy way to convert from one of these to the other. Sometimes what people call this is like compressed or compact QR versus full QR or something like that. And it depends on, it depends on the application that you have, right? So sometimes you just want a basis for the column space, in which case you probably want the compressed thing. Other times, like maybe you want some other thing, you want like a full rotation matrix, and then you need the larger one. Yeah? Probably for least squares, you want the compressed QR because it takes less space. Yeah. All right, so we're low on time. Hamid, maybe if you have a question, you can talk to me after class. With that, oh yeah, that's our last little detail here. Right, and actually we've basically already covered all this. Yeah, so that's the end of our discussion of QR. Next time, we're going to embark on a multi-lecture journey together to talk about eigenvector problems, which is going to be sort of the next segment of this course. So with that, I will see you on Wednesday. Have a delightful Monday afternoon. Get out of my classroom.